Weijie Su from Wharton. If you want to tell us about connections between FDR and robustness.
First, I want to thank the organizers for inviting me and also bring together people from different backgrounds so I can learn and talk. And also thank for Kiara's talk. I guess will make my talk much more accessible. So still warm up again, and FDP is defined as a ratio of false discoveries among all the discoveries you make. So this is an example. Sorry, it's not very clear. So this is your estimated model. So you make 300 discoveries. So denominator is 300, but 200 are false. So numerator is 200. So this is FDP, and FDR is the expected value of FDP. And we want to control FDR below, say, Q 5% or 10%. So Q usually we call it nominal level. And it was proposed by Benjamini and Hochberg. So this procedure actually is, in addition to FDR, they also proposed a procedure for controlling FDR. Let P1 to Pm denote all the M p-values. And this procedure is very simple. First, we order the p-value. It just make R to be the largest such that at least the R of these p-values are below Q times R over N. Q is the nominal level. And then BH reject all the R smallest p-values. So this is the procedure. Here, maybe say something people have already are very familiar. P-value here is a measure of how extreme the observation is, if your null is true. And in our setting, you can imagine that we observe Y following a normal distribution, and you are testing whether the mean is 0 or not. If the ground truth is mu is really 0, we call the p-value a null p-value. Otherwise, we call it a non-null p-value. So this is our setting. Here is an illustration of BH. How does it work graphically? We first sort the p-values from the smallest to the largest. So they are our treasure. Good p-values, they are the bad p-values because they are large. And then we draw a threshold proportional to J, the index. And the last, we reject the p-values below the cutoffs. Here we reject from the right to the left. So it's a step-up procedure. So this is the last rejection. All the red ones are declared significant. They are our discoveries. So the BH procedure, in the original theorem, they proved that if the nulls are jointly independent, the null p-values are independent from each other. And the second, as a whole, the null p-values are further independent of the non-nulls. Then they can control FDR, provably, below Q. And later, Benjamini and Iacotelli, they relaxed the independence, the two independence conditions by some sort of positive dependence. So this is basically the state of art. So you see, the conditions are very stringent because it's really hard to imagine that the real dependence are positive, right? And so arbitrary for real problems, most likely they will violate the conditions for FDR control. The impact of FDR and the BH is huge. It's perhaps the most popular error rate in genomics. 2 days ago, the citation of the original paper has reached almost 50,000. So every month, they will receive about 600 citations, about the same of my whole citations. And certainly the impact of FDR is beyond statistics and biology. In summer 2014, two computer scientists became interested in FDR. They are Sincere and Lee. And now Sincere is at Harvard, Lee is at Google. About 4 years ago, they were research scientists at Microsoft Research, Silicon Valley. And I spent a wonderful summer there working with them. Unfortunately, their lab was closed right after I finished my internship. It's a sad story anyway. So what I was there doing is to prove FDR control of a...
Weijie does not have anything to do with your work.
Yeah, it has nothing to do with me. Yeah, but I don't know. It's only because there's no potential outcome. Only me. Yeah. There's no true words. So I was there to prove FDR control of a version of BH. It's a differential private BH. Here, differential privacy has nothing to do with the rest of the talk. So it was challenging, very simple, because smallest p-values may not be selected because of randomness. You add noise to your p-values, then you select the noisy smallest p-values. So that's why it makes it challenging. Existing proofs like martingale techniques of Story et al. And the Leibowant technique of Benjamini and Hochberg, they all require a property that you set threshold below it are all rejections. Here does not satisfy. Okay, we cannot work here. As it's a kind of hindsight. As you will see, this is because existing procedures do not explore the robustness of the procedure. And actually, this is the whole point of the talk today. So the theory and the practice of FDR actually is very contradicting to me. The theory is very restricted. Only under very restricted conditions, FDR can be controlled at a reasonable level. But in practice, it works so well. People just use it in practice. I've done simulations. And it's really difficult to find a correlation structure to violate FDR control. Extremely difficult. So why? Why there is such two contradicting facts? So this talk, we will give some evidence why there is such big gap. So the conclusion is very simple. BH as a procedure, we want to argue that it's robust. And FDR as a notion of error is also robust. And we will show 3 points. First, what's robust here? Here we say the robust is robust to dependence between nulls and the dependence between nulls and the non-nulls. Does not matter too much. And the null distribution matters most in FDR control. And the last, we will propose a new relaxed criterion called FDR consistency. So first part, how does robustness arise? This is condition, very simple. A procedure is called compliant if any reject p-values, even the largest reject p-values is below q times r over n. So this is by almost a definition of BH, right? So the threshold depends on the rank, depends on how many discoveries you make. R is the number of discoveries, essentially the number of rejected p-values. However, you see in this definition, you can skip some small p-values. That's not necessarily the case that any p-values below the threshold must be rejected. No, you can skip some of them. Actually, this is a special example of self-consistency condition proposed by Blanchard and Roquan. Here, by definition, you see BH is compliant. And many variants of BH actually are also compliant. It's almost a very natural definition. The compliance actually immediately implies some property on FDP. FDP is always bounded by this quantity. So P naught 1 to P naught M0 are all the ordered null p-values. Here M naught denotes the total number of null p-values. And how to prove it? Actually, it's very simple. First, let's denote V by the number of false discoveries. Then the largest rejected null p-value must be look like this, right? Because this is smallest V smallest null p-values. They are at least V of the rejected. And then by compliance, this p-value must be below Q times R over N. So R must be lower bounded by this number. So now FDP, by definition, V over R must be smaller than that. So V here is mass between 1 to M naught. So by the way, V can be 0, right? V can be 0, then this is always non-negative, and this is 0. So if V is 0, it's still satisfied. So this is a very simple fact. And here, we can actually, later we will consider a notion of FDR where we only penalize if we make at least K false discoveries. The original FDR is just the case of K equals 1. In the previous kind of proof, you will see that the non-null p-values actually does not match at all, right? So meaning that actually the non-nulls, you can construct the non-nulls adversary after looking at the nulls. You can do whatever, and this quantity will always satisfy. So this means that the FDP actually is intrinsically is a bound, it's a property of the null p-values. And now how can we leverage the compliance for us? Let's propose a condition, a little bit redundant because this definition is so simple. We use IWN instead. A set of p-values has satisfy IWN property if the null p-values are jointly independent. That's it. Only concerning the null p-values. Allow me to use a fancy IWN abbreviation for this property because this is so trivial in some sense. Okay, so we have a theorem. The theorem saying that for K should be at least 2, then FDR is bounded by a constant times Q, nominal level, for any compliant procedure, so including the BH, of course, if the p-values are satisfy IWN property. It of course applies to many BH variants because compliant condition is very natural. And the constants here, like C2, C3, C10, can be given by some formula, as I will show you later. And they will decrease if the K is large, decrease to almost 1 if K is really large. Here the dependence between nulls and the non-nulls can be adversary, just by the definition of IWN, does not say anything about the non-null p-values. So maybe to explain why BH is robust. At least robust to the dependence between nulls and the non-nulls. So this is optimal. The constant is optimal, meaning that if you choose a smaller constant, say, and the Q is small enough and the M is large, the dimension is large enough, then there must exist a compliant procedure and certain IWN p-values such that FDR K can be larger than CQ. And now let's make connection to the literature. So the state-of-art FDR control requires positive dependence between nulls and the non-nulls. And this is called PRDS. I will review the definition later exactly. And for arbitrary dependence, you can show that the FDR can be as large as basically log m, the dimension, times Q. So can be very large. And in my last time I told about this, Chiara pointed to me that a recent work of Jean and Aditya, so they actually derived similar related results on robustness of FDP bounds. Basically, they are saying you can achieve uniform FDP bounds if you do, you can stop anywhere you want. Now let's prove it. Very simple. So first, this is compliance implication of the compliance condition. And since we assume that the p-values are independent, then we can replace the null p-values by the IID uniform order statistics. So U1 to UM0, they are the order statistics of uniform random variables between 0 and 1. So look like this. Okay. So essentially, we only need to prove that this constant, this quantity is bounded below by a constant only depending on k, regardless of n. And this is actually very simple. You can show that this number actually is an increasing number of n. If you make n larger, it will only increase. The proof is actually very simple, so I will skip it. And so now, essentially, did I say anything? So essentially, you let n to be infinity. So this is your constant. And this constant actually looks like this. You see, it's decreasing function of k. If k is very large, then it will slowly approach 1. And you can also consider a variant. Actually, I don't know people really use it. If you make at least k rejections. This is nice. Actually, you know k, you know r, right? So you know when to penalty. For the previous FDR k, you don't know when to penalize because v is in principle is unknown. So here, if k is at least 1, then still IWN p-values. Then any compliant procedure will control FDR k at this level. Okay, so the proof actually is similar here, but we use a martingale. So now let's do some simulations. And so here is a Gaussian means problem, and we make the covariance matrix of the diagonal to be negative. Okay, actually this is the most negative can be. Otherwise, it will not be positive definite. So the nominal level is 10. So. By the way, so this does not satisfy PRDS because PRDS requires that the covariance matrix in the off-diagonal should be positive, and in principle only applies to one-sided test. So here, I think we do two-sided test. This is original FDR, this is FDR2, and we let the number of non-zeros, M1, varying from 100, almost 1 to 500. And you see this is the cutoff, this is a nominal level, 10%. They are basically always below the nominal level. So actually there are tons of such simulations in the literature, and I also have done this. And it's really hard to violate FDR actually, FDR control. And here now we consider kind of t-test. We observe like such 10 such vectors, and we do a t-test for each component, and the results similar. Here you see the FDR will be decreasing. This is because the true null proportion is decreasing if you increase the number of true effects. Okay, anyhow, they were always below the nominal level. So now let's go to the second part. And so here, what we have done so far is that if we are happy to lose a constant, then we control FDR in this case. So as long as between the nulls, they are independent, and between nulls and the non-nulls can be adversary. And between the inside within the non-nulls even can be arbitrary adversary. In this case, we control FDR. So it's robust to what? Robust to two things. The dependence between nulls and the non-nulls, robust to the inside within dependence of the non-null p-values. Let's review what is PRDS. PRDS essentially is the condition is a little bit complicated, but roughly speaking, that if you increase one component of xi, then the rest of the components of the vectors will also increase. And here I should be any null p-value component. And then using a very kind of leave one out proof by Benjamini and Iacotelli, it's a very beautiful proof. They say if the p-values satisfy PRDS, then FDR is bounded exactly at Q, level Q. So this is the FDR control word of PRDS. Here you see they only allow the dependence within the non-node to be arbitrary, and but within the node should be positive, and between the two paths should also be positive. So this is what PRDS says. So, and then now let's take a union, and this is kind of what's the current provable FDR control world. Here, original, and this is what we did. And of course, they overlap a little bit, right? So this is our current FDR control world. And now can we extend the FDR control world? Meaning that we still leave this arbitrary and leave null and the non-null dependence to be arbitrary, and relax the independence condition to positive condition. Can we do it? So this is the rest part of the talk. Actually, it's based on very simple observation. So this is still the compliance condition. And now let's remove everything in the denominator. The denominator actually takes this form. Well, maybe this is what reminds you the Sims test. Actually, what's the distribution of this statistics, of this number? If we can lower bound the distribution of this random variable, essentially we can derive a upper bound of FDP, right? And this actually is very related to Sims test. So here, let's propose a new condition. A set of p-values are said to satisfy positive regression dependence within nulls, PRDN. So here we replace the last s by n. If the nulls satisfy, only the nulls satisfy PRDS, meaning that only the nulls are jointly positive, have positive dependence, regardless of the dependence between non-nulls and nulls. So this includes both PRDS and the IWN as special cases, and no assumptions regarding the non-nulls. And on the PRDN, we can show that this random variable actually is stochastically larger than or equal to uniform. Why? Actually, this is actually it's just a consequence of the PRDS condition. Because why? If you restrict your BH on the null p-values, you will see that this is actually, if this is the probability that this is smaller than Q, it's just the FDP, just FDR. So by definition, PRDS on the global null should control FDR. So this actually is stochastically larger than uniform. And the proof actually is very simple. Actually, it's already there. This connection to Sims, because if this statistic is smaller than the nominal level, then we reject global null. This is what Sims does. Okay, so here is our theorem. We are saying that if a compliant procedure applied to PRDN p-values, and then FDR is controlled at this form. The proof actually is just several lines. First, this is the compliance condition. And second, we make this random variable larger, replaced by the uniform. Okay, this is uniform between 0 and 1. Then, by integration, look like this. So this is nothing fancy. However, this condition, actually is optimal. In some sense, if Q is sufficiently small and M is sufficiently large, then we can find a compliant procedure. Sorry, this is a typo. I should say there exists a compliant procedure applied to certain PRDN p-values. The FDR will be larger than the C. This is, in some sense, optimal. Is it possible to get rid of the log factor? It's a little bit annoying. And this actually really from the adversariness. If we are happy to bound adversariness a little bit, meaning that you can still be adversary, but suppose you are masked, meaning that you can have only access to the all sorted p-values, but the smallest one. Okay, so this is exactly the case where you cannot perform Bonferroni correction. In this case, actually, you will be fine. FDR is bounded by 3 times Q. So that's really adversary from looking at the smallest p-values. And now this is our current FDR control world. We basically allow both parts to be adversary and within the nulls to be independent, positive correlated. Okay, so we take a kind of big union, and this is our provable FDR control word. And the last part, we will introduce a new notion, a relaxed notion of FDR. Here, our observation is that, look, if we let Q to be 0, this will converge to 0, and independent of the dimension. However, in the worst case, in the worst dependent structure, the level is log n times Q. If you let Q to be 0, it will still tend to 0, but depends on the dimension. It's not uniform over the dimension. Here we propose a new notion of FDR. Actually, I want to stick your suggestion. I'm not sure whether it's really, really meaningful. Our saying that a dependence of structure, a series, index of the by dimension, is said to be FDR consistent if the FDR of any compliant procedure satisfies that FDR is below f of Q. Here, f can be any function as long as it will converge to 0 uniformly over the dimension. So this is what we call FDR consistency. And if the dependence of the nodes is positive, then as we know, it's consistent. So we have show it. In the worst adversary dependence, FQ can be as large as log m times Q, then certainly it's not FDR consistent. What's the motivation to propose this relaxed notion? It's because that if we are happy with this relaxed notion, we don't need to bother with the non-nodes at all. The result saying that if the non-dependent structure is FDR consistent, then if you combine the non-nodes, the whole dependent structure will be automatically FDR consistent. So this means FDR consistency actually is robust to adversary nodes. And if this is really meaningful, to suggest us to focus on the nodes. Let's prove it. Actually, very simple. Based on this lemma, FDR 0x is the FDR level if we let the compliant procedure restrict on only the null p-values. And then the full FDR, if you apply to the full p-values, will be bounded by in this form. The proof actually very simple. First, there's the compliance condition first, and then we know that the CDF of this random variable in the denominator is bounded by the FDR not of Q given by the condition. And the last fact, then we can use kind of integration by part to write down to get this lemma. The last step is to show that if f of x is convergent to 0 uniformly over n, then the whole quantity will also converge to 0 if Q tends to 0. So the proof actually is also elementary. So this is our picture. If we are interested in FDR consistency to extend this word, we only need to focus on the dependence of the nodes. That's it. So far, we can show that if the dependence of the nodes are positive, we are happy. But maybe we can relax it. So looks like FDR consistency is really a weak notion, but actually not always. I found a counterexample. It's a problem due to Williams of Jones and Tukey. So they observe independent Gaussian means problems. So mu1 to mu(n) can be different. So the question is to test the pairwise difference if mu(i) is mu(j) and mu(j) are equal or not. So this problem. So look, actually dependence this is a very independent problem because you randomly select two edges on the graph. Actually, they do not share any node, right? Then they are independent. A recent paper of Liu et al. Showed that FDR actually is controlled if at least one mean mu(i) is significantly different from the others. So the question is that if all the mu(i) are equal, then on the global null, is FDR consistency the case or not? Actually, my original goal was to prove yes. I tried very hard to prove that it really controls FDR in the weak sense. However, I failed. And later on, maybe I thought that maybe it's the opposite. So actually, I quickly get the proof. The proof saying that under the global null of the problem of Williams, Jones, and Tukey, the dependence structure under the global null actually is not FDR consistent. Even though most edges are independent. It's an almost independent structure. However, it's still not FDR consistent. So this is summary. And here we want to argue that FDR and the BH are both robust to adversary dependence, especially between the nulls and the non-nulls. And the second, we show that the joint distribution of the nulls really matters most, especially if we are interested in FDR consistency. FDR control is extremely hard. And if it's really hard for you, maybe actually we can consider FDR consistency as the starting point. So this is the reference, and thanks for your attention.
We'll have plenty of time for questions. I have a question about the constants. Right, so like how important are the constants here? In particular, the log Q that you got, is it actually 1 times log Q?
Yeah. It's Q times log of 1 over Q, right?
Yeah. Is it 1 times log 1 over Q?
Yeah. So this Q times log 1 over Q. Actually, if Q is really small, it can be large. Yeah. If Q is 1%, then log 100 is basically 5, right? Yeah.
It's more like of a meta comment maybe. If we open the book by Brad Efron, then we'll see a statement like this. That is, under dependence, which is a bit this your talk, FDR is control. And in fact, if you look at the Bayes and empirical Bayes explanation of it, it's pretty clear from the empirical Bayes viewpoint that you control FDR even if you have dependency. But what Brad argues is that the estimate of FDP is very bad. It's extremely volatile. And so you may end up with a procedure that, yes, controls the FDR even under dependence, but is not really useful because the FDP is like all over the place. If you see what I'm saying. Like a procedure that might control the FDR says, reject everything 10% of the time, 0, nothing, 90% of the time. That controls the FDR, but that's not a useful procedure. And that works under any form of dependence. So when we're so Brad's point is that under dependence, the estimate of FDP is not great. And so that's why you see enormous variability in your FDP. And that says that maybe controlling the FDR is not good enough. And so when we think about extending the Benjamini-Hochberg theory to the dependent case, how far along do we want? Because there's a point at which controlling the FDR is not meaningful. And so have you given any thoughts about what kind of dependence, because, do you see what I'm saying? Like, what kind, there are places you do not want to go because I don't think that the FDR is criterion easy answer.
Yeah, actually a very good comment. So actually we can look at this term. So the annoying term, actually the existence is Q times log 1 over Q, right? Where does it come from? Actually, as you said, comes from some events that FDP can be huge, but most of the time actually it's Q. So this is a good suggestion. Maybe we can further see some robustness of FDR control things if we care about the quantile, because the contribution of FDR from the tail event actually can be huge here.
So,
Hi, Peter.
regarding this comment, so it's kind of funny also under the positive regression dependence, right? I mean, there are some proofs now and some guarantees. And so under the negative dependence, it seems to be hard from a theory point of view. But the negative dependence should be less adversarial to the whole story, right? For example, the variance would not explode under negative dependence. So there seems to be some sort of interesting views on this too, that actually negative dependence is maybe hard from a theory point of view, but it's not so adversarial to the concept. So does that make sense? Or?
Yeah, exactly. Actually, positive dependence is the regime where we will observe very large p-values simultaneously or small p-values simultaneously, right? And the negative correlation actually makes them even. So actually this is in some sense ideal FDR control. FDR is the average sense. But it's really, I think it's a technical artifact and somehow, so that's why actually the leave one out proof actually is really cute. It's really hard to generalize beyond the PRDS.
No, but I mean, I think what Peter and I were saying is that there is a place where a form of dependence is going to really tell us that we don't want to use FDR, that it's not a good measure.
Yes, that's
I know that if I repeat that I care about this experiment, and you know, it's either 0 or 1, I have no way to tell really.
Yes.
And so what do I do with a procedure like this?
Yeah, yeah.
And is there could be research on, you know.
Yeah. Have a minute.
So I didn't hear so all the comments over there. So so just to kind of ask broadly, if FDR is not the right thing to control, did you say there was an obvious alternative, or is this the question? What is the alternative if there's some odd dependence that makes it not work well?
Yeah, people propose various notions to make it robust. For example, FDR existence. You basically control the probability that your FDP is above some threshold, like 5%, say 5%. And then you consider the tail probability. You are happy with the case where FDR, ultimately we are interested in FDP. So FDP is a random variable. FDR is only the expected value. And here, maybe I think using the compliance condition may give a sense, because compliance gives an upper bound of the FDP. If we can control the tail probability of the upper bound, automatically we control the upper bound of the FDP. And so that's why actually the compliance condition actually is really useful.
All right, let's thank the speaker again.